Hello students, welcome back to the classroom point. In our previous class, we discussed the solutions topic regarding the vaporization, vapor pressure and boiling point. Today we shall discuss the lowering of vapor pressure, relative lowering of vapor pressure and colligative properties. There Raoult's law, about the two type of the Raoult's laws are there, solid in liquid as well as the liquid in liquid type of the solutions. So let us see all these discussions in this today's class. So we shall begin the class with the lowering of vapor pressure. And those who do not see the previous video, better see that previous video also. Why? Because today's video is the extended part of that video where vaporization and the condensation process being discussed there, and its applications today we are going to discuss it. So let's discuss that. Lowering of vapor pressure. This lowering of vapor pressure can be represented by delta P or P naught minus Ps. So here the name itself showing that lowering means a decrease in vapor pressure. So whatever the concept we are going to discuss, there shall be decrease in the vapor pressure of the compositions. So let us see here. When you take a normal solvent, a pure solvent, so in this pure solvent, the entire surface area is occupied by the only solvent molecules. And we know that vaporization is the surface phenomenon. That means only surface molecules participate in the vaporization. So that here the solvent molecules, only since solvents are present on the surface area, all these molecules participate in the vaporization process so that they can create the more vapor and also vapor pressure. So the vapor pressure of the pure solvent is taken as P naught. Now to this let us add some amount of the solute. Imagine 1 gram of X solute I am going to add. So when this amount of solute is added, this 1 gram of X non-volatile solute. So non-volatile in this sense, this solute whatever we are going to add should not have the ability to evaporate. So when non-volatile solute, some amount of the non-volatile solute is added, when it dissolves into the solvent, it will create the composition, mixture of the composition, that is what called the solution. So in this solution, both the solute particles as well as solvent particles are present. And the solute particles not only present in the bottom of the flask or beaker. Since we are discussing about the homogeneous solution, so in homogeneous solution, the solute particles uniformly distributed throughout the volume of the solution. Hence, they also occupy the surface area. Some of the surface solvent molecules are being replaced by the non-volatile solute particles. Now, from solvent to the solution, number of solvent molecules on the surface area gradually decrease. When number of solvent molecules decrease, we know that vaporization comes only from the solvent molecules because only the solvent is the volatile here and solute is non-volatile. As the number of solvent molecules decrease, vaporization also decrease, means number of liquid molecules converting into the vapor also decrease. Then vapor decrease, number of vapor molecules decrease and its pressure also decrease. The pressure exerted by the vapor also decrease as the number of vapor molecules decrease. So the vapor pressure of the, now this is called as the solution, vapor pressure of the solution I am taking it as a PS. Imagine initial vapor pressure of the solvent was 760 millimeters of Hg or is equals to 1 atmosphere, that is also equals to 1.03 bar. Now here vapor pressure of the solution. Solution vapor pressure is less than the vapor pressure of the solvent. Let us take the vapor pressure of the solution as 700 millimeters of mercury. This is 101. 101.325. So here the vapor pressure of the composition is less than the vapor pressure of the solvent. So here we can conclude one point that the vapor pressure of the solvent is always greater than the vapor pressure of the solution that containing the non-volatile solute. Instead of this 1 gram of the non-volatile solute, what happens if you add the 2 grams of non-volatile solute? Now, some more number of the solvent molecules from the surface area being replaced by the solute molecules. Hence, again vaporization still drops, vapor pressure also still decreases. Let us take this solution as the second solution, whose vapor pressure is approximately, let us imagine, 650 millimeters of mercury. That means still decreases. So from this we can clear one thing, that when the amount of the solute in a solution increases, the vapor pressure gradually decreases. When the amount of the solute in the solution increases, its concentration also increases. That means when the concentration of the solution increases, vapor pressure gradually drops. Then what is the difference between these vapor pressures? 760 minus 700, that means 60 millimeters of Hg. How did we calculate? Higher value minus lower value. What is the higher value? P0 value. What is the lower value? PS. So this difference, this is also pressure, this is also pressure. The difference of the two vapor pressures can be taken as delta P. So delta P is nothing but P0 minus PS. That means how much vapor pressure is decreased. That is what called the lowering of vapor pressure. As from this particular diagram, when the concentration of the solution increases, vapor pressure gradually decrease. So in this case, vapor pressure drop is only 60 millimeters of mercury. But in the second case, the vapor pressure drop is approximately 110 millimeters of mercury. That means more the solute, more drop in the vapor pressure of the solution. So that we can say that delta P value is directly proportional to the particle concentration or concentration of the solution. When concentration of the solution increases, then decrease also increase. That's why we can say that delta P value is directly proportional to the concentration, and its units are atmospheres only, because pressure minus pressure giving the atmosphere, again pressure units only. Now let us take the two different solutions. So in the first solution, I am going to take the 1m urea solution, and second one I am taking the 1m of NaCl solution. Now the question is, are they having same amount of the lowering of vapor pressure? It is not. The reason here is, here urea is a non-electrolyte. Whereas NaCl is an electrolyte. Non-electrolyte means it will not dissociate into the ions, whereas electrolyte means it will dissociate into the ions. So 1m urea stands for the 1 mole of urea molecules. 1 mole of urea molecules are present in the solution. But in this case, 1 mole of NaCl formulas. 1 mole of NaCl means, see, NaCl, when you dissolve into the water, it dissociates into Na plus Cl minus ions. 1 mole is giving 1 mole of Na plus ions and 1 mole of Cl minus ions. Total number of particles are equals to 2 moles of ions are there. That means number of particles suddenly increase. When the number of particles increase, so this solution behaves as the more concentrated solution compared to the 1 mole urea, 1 m urea solution. Molarity wise these are having the similar concentration, but particle wise this is having the higher concentration. Solutes particles are more in this case compared to this one. That's why now the question is how to calculate the particle concentration. Particle concentration is equals to given concentration. You can take the molarity or molality. So whatever it may be, given concentration, I am taking the molarity into number of ions or number of particles produced by that particular solute. Now, if you see this between these two, here 1 mole of urea, imagine 1 mole of urea is giving the only 1 molecule of the urea particle. Just imagine. So that here only 1 urea molecule is present. Here NaCl is giving the 1 mole is giving the 2 moles of particles, so that 2 particles are occupying the places. So here number of solute particles are more in the second case compared to the first case. That's why here vaporization is less, vapor pressure also less, and difference value increases. That's why the lowering of vapor pressure is directly proportional to concentration. So lowering of vapor pressure value higher for this NaCl compared to the urea. So that we can say that 1 m urea less than the 1 m NaCl. Vapor pressure is more here, vapor pressure is less here, but difference is less here, difference is more here, because the concentration of the solution gradually increases. Now if you take the 0.1 m NaCl, 0.1 m BaCl2, 0.1 m AlCl3, so we can say that where the more difference in the lowering of vapor pressure is noticed means, in this case, every time you have to multiply the concentration with the number of ions given by the solute, so that here NaCl is giving the only 2, so that its particle concentration is 0.1 into 2 equals to 0.2. Here 1 Ba2 plus and 2 Cl minus and, so that the value is equals to 0.3 m. Here Al3 plus and 3 Cl minus, and that means totally 4 are there. So 0.4 m particle concentration is more, so the lowering of vapor pressure also more. Now let us take 2 solutions in a sealed beaker and how this pressure is observed. So I have taken the 2 beakers. These 2 beakers are sealed in a closed container. They are in the common space. But these 2 are open beakers sealed in a closed container. So in one beaker number 1, and this is a beaker number 2. So in first beaker I have taken the solvent. Second beaker I am taking the solution that is containing the non-volatile solute. Then obviously both will try to create the vapor pressure and vaporization, but we know that the vapor pressure of the solvent is more than the solution, because in the solvent only solvent molecules are present on the surface area. That's why their vaporization also more. So before solution is occupying the entire space, solvent molecules occupy the most of the space available compared to the solvent vapor molecules coming from the solution, because the vaporization is more in the solvent. Now vaporization taken place and most of the space occupied by the solvent molecules. After vaporization, the reverse process also takes place. The reverse process is the solvent molecules or the vapor molecules collide with each other and also with their surfaces. So here whenever the solvent molecules collide with the surface of the liquid, they start converting back into the liquid state. That process we call as a condensation process. Vaporization takes place in both areas, but vaporization is more from the solvent side. Vaporization is less from the solution side. That's why most of the space occupied by the solvent molecules, but condensation happens on both sides. So when condensation happens on both sides, most of the condensation is nothing but the conversion of the vapor molecules into liquid state. So most of the vapor molecules are from the solvent only. That's why most of the vapor molecules start participating in the condensation process. So that after some time, if you notice that the volume of the solution gradually increases and the volume of the solvent gradually decreases. Because indirectly vapor molecule solvent is transferring from the solvent to the solution in the form of the vapor. Now, let us take the two different solutions instead of the solvent and solution. When you take the two different solutions of one is 0.01 m urea solution, 0.1 m urea solution. 0.01 m means this is a low concentrated solution. When concentration is less, vaporization is more, because concentration less means more solvent is present, less solute is present. Vaporization is more here. When concentration is more, so that this is high concentrated solution, vaporization is less. So when low concentrated solution and high concentrated solution are enclosed in the same common container, again the solvent molecule starts flow from the low concentrated solution to the higher concentrated solution in the form of the vapor, so that the volume of the more concentrated solution gradually increases and a low concentrated solution gradually decreases. So this is about the lowering of vapor pressure. So lowering of vapor pressure basically depends on the quantity of the solute that we are adding, but not on the nature of the solute or the identity of the solute. What is the nature and identity of the solute? The question arises, instead of the NaCl, what if you take HCl or NaOH? Here NaCl is giving the 2 moles of ions. One NaCl dissociates into Na plus Cl minus ions. Next, HCl dissociates into H plus and Cl minus. Let us imagine it is undergoing the complete dissociation. And NaOH dissociates into Na plus OH minus ions. So here NaCl is a salt, HCl is an acid, NaOH is a base. Even though they have the different natures, but the number of particles produced by each of these solute particles is similar. That's why the lowering of vapor pressure is not exactly equal, but also similar. Why it is not exactly equal means the hydration process means the interaction between the ions and the solvent molecules differs from the solute to the solute. That's why the lowering of vapor pressure may not be exactly equal, but we can say that it is almost similar. So that's why NaCl, HCl, NaOH, lowering of vapor pressures are close to each other because they are producing the same number of ions. That is the reason we can say that lowering of vapor pressure is depending only on the quantity of the solute, but not on their identity. When the number of particles changes, automatically lowering of vapor pressure and concentration values also changes. Now let us see the relative lowering of vapor pressure. Relative lowering of vapor pressure, it can be written as delta P by P naught. So it can also represent usually as RLVP, relative lowering of vapor pressure, instead of writing the entire sentence every time. So we can take the mnemonics that only letters. So what is relative lowering of vapor pressure? We already discussed about the lowering of vapor pressure. Relative lowering of vapor pressure means you are comparing how much decrease of the vapor pressure happened when you compare with the pure solvent vapor pressure. You are relating. That is what called the relative lowering of vapor pressure. So relative lowering of vapor pressure, RLVP, is nothing but the ratio between the lowering of vapor pressure to the pure solvent vapor pressure. Or else this can be written as P naught minus Ps by P naught. This is what called the relative lowering of vapor pressure. So you are comparing every time, means every time we take the ratio of the decrease in the vapor pressure values with respect to the vapor pressure of the pure solvent. That is what called the relative lowering of vapor pressure. Now what other factors we can understand from the relative lowering of vapor pressure? Relative lowering of vapor pressure has no units. See here, P0 minus Ps gives the pressure units. Pressure by pressure is equals to no units. Atmospheres cancel out, so that it has no units. And independent of temperature. But lowering of vapor pressure depends on the temperature. This particular point we shall discuss in the Raoult's law for the solids and liquids, so that there you will get the clear picture how it is not independent of, it is independent of the temperature. And what is the relation between the relative lowering of vapor pressure and the concentration, like particle concentration? We can say that RLVP, relative lowering of vapor pressure, is directly proportional to the particle concentration. Why it is directly proportional to the particle concentration? We have already seen that lowering of vapor pressure is directly proportional to the concentration. When concentration increases, lowering of vapor pressure, that means delta P value also increase. So in this formula, delta P occupies the numerator position. So when the numerator value increases, the total value also increases. Why? Because the denominator value is constant here. So that is the reason why we can say that relative lowering of vapor pressure is directly proportional to the concentration. Now let us see the colligative properties, in which relative lowering of vapor pressure, how it is independent of the temperature. So colligative properties. The definition of the colligative properties is, these are the properties that depend only on number of solute particles but not on their nature. So the properties of the solution which depend on the number of solute particles but not on the nature of the solute particles are known as the colligative properties. As we discussed earlier, NaCl, HCl, NaOH, both are having the same number of solute particles, but nature is different. So as long as the number of particles remains same, then automatically colligative properties are also remains similar, almost same. Let us see what are the colligative properties and which properties depends only on the number of solute particles but not on the nature of the solute particles. So they are, first one is relative lowering of vapor pressure. Second one is elevation in boiling point of solvent. Here also relative lowering of vapor pressure of solvent. Depression in freezing point of solvent. Fourth one, osmotic pressure. Of solution. So the notations for this elevation of boiling point of the solvent is delta TB. This is delta TF. Osmotic pressure represented by the symbol pi. So this about these three we shall discuss in the coming classes. Today we shall discuss about the relative lowering of vapor pressure of the solvent, how it is a colligative property. This is also known as Raoult's law for solid in liquid type of solutions. Solid in liquid type of solution. Already we discussed the how vaporization and vapor pressure is affected by the adding the some amount of the non-volatile solute to the solvent, so that automatically evaporation decreases, vapor pressure also decreases. So based on that only, Raoult has proposed a relation between the vapor pressure of the solution and the vapor pressure of the solvent and also mole fraction of the solvent. Now let's come to the point here. Whenever we take a particular solvent in a beaker, evaporation occurs. By adding some solute particles, evaporation decreases. Why? Because this evaporation occurs only from the solvent molecules on the surface area. When you add some more amount of the solute, this evaporation still decreases. That means these particles, whatever the non-volatile solute particles are added, they are not participating in the evaporation. Only solvent molecules are participating. So more the solvent molecules on the surface area, more shall be the evaporation and more shall be the vapor pressure exerted by such vapor on the solution. That means the vapor pressure of the solution, whatever we are going to discuss, depends on the number of solvent molecules on the surface of the solution. So he has given a relation between all these three parameters and saying that the vapor pressure of a solution is directly proportional to the mole fraction of the solvent. When solvent molecules increase, evaporation increase, vapor pressure of the solution also shall be very higher. And from this we can derive one more thing, that PS is equals to P0 into X1. Why proportional symbol is replaced by the P0? Why? Because P0 is the vapor pressure of the solvent at that particular temperature and it remains constant as long as temperature remains constant. That's why PS is equals to P0 into X1. So Raoult's law has many definitions. So we shall see one by one. In that, first definition is this one. The vapor pressure of a solution is directly proportional to the mole fraction of the solvent. Second definition is this one. The vapor pressure of a solution is equals to the product of vapor pressure of the solvent and mole fraction of the solvent. Now let us try to send this P0 value the other side so that we get the PS by P0 is equals to X1. This is the third definition, in which the ratio between the vapor pressure of the solution and its solvent is equals to mole fraction of the solvent. It is also known as the Raoult's law. And let us try to see how we can mathematically transform this formula. We know that some of the mole fractions are always equals to unity x1 plus x2 is equals to 1. And let us try to convert this one, x1 equals to 1 minus x2. So now I can substitute this value here. So we can get PS by P0 equals to 1 minus x2. Now rearrange the equation so that 1 minus one side and x2 one side. So we get the 1 minus PS by P0 is equals to x2. And now we'll get the P0 minus PS by P0 is equals to x2. This is also called the Raoult's law, but here it is called the relative lowering of vapor pressure. Now, this is the fourth form of the Raoult's law, which says that P0 minus PS by P0 is known as the relative lowering of vapor pressure. So, the relative lowering of vapor pressure of any solution at a given temperature is equals to the mole fraction of the solute. Till now, we defined the Raoult's law using the solvent. But now onwards we are going to define the Raoult's law using the mole fraction of the solute. Now this value we can change again into we can convert mathematically into the P0 minus PS. Send the P0 value the other side so that we will get the P0 into X2. This P0 minus PS is nothing but the delta P is equals to P0 into X2. Now the Raoult's law fifth form is P0 minus PS means it is known as the lowering of vapor pressure. Lowering of vapor pressure is equals to the product of vapor pressure of the solvent and mole fraction of the solute. Now you should not get confused between this form and that form. Here it is about the vapor pressure of the solution is equals to the product of vapor pressure of the solvent and the mole fraction of the solvent. Here the lowering of vapor pressure is the product of the solvent, vapor pressure of the solvent and the mole fraction of the solute. Now let us try to replace this P0 value using the proportionality symbol so that we can write down the delta P is directly proportional to the mole fraction of solute. This is the sixth form. So Raoult's law says that the lowering of vapor pressure of a solution is directly proportional to the mole fraction of the solute. Remember, it is not equal, it is directly proportional. If you want to use the equal symbol, means P naught value has to be substituted here. If you want to define the Raoult's law of solid and liquid type of the solutions, then you must use this relative lowering of vapor pressure also. So in terms of relative lowering of vapor pressure, you can see equal. Relative lowering of vapor pressure is equals to mole fraction of solute, but lowering of vapor pressure is directly proportional to the mole fraction of solute. Now, let us try to see how this relative lowering of vapor pressure is connected to the molality. What is the relation between the molality and the relative lowering of vapor pressure? So for that, let us try to expand this equation. P naught minus Ps by P naught equals to x2. x2 means number of moles of solute divided by number of moles of the solvent plus number of moles of solute. All these colligative properties are applicable for the very dilute solutions. Concentrated solutions, we cannot identify much difference values. That's why for dilute solutions, means the amount of the solute present in the solvent is very, very less. Such type of the solutions are called the dilute solutions. So for dilute solutions, obviously the number of solute particles are less when compared to the number of moles of the solvent molecules. So that is the reason why we can neglect the N2 value from the denominator. Remember that you cannot neglect the N2 value from the numerator. If you neglect, it will become 0. Nothing will be there. So N2 from the denominator can be neglected, and because this is the highest value, this is a negligible value. So the equation can be written as P naught minus Ps by P naught equals to number of moles of solute by number of moles of solvent. And in mole fraction, we discussed that x2 by x1 is equals to number of moles of solute by number of moles of solvent. This form also you can write down. That is a different part. Ratio of number of moles gives the ratio of the mole fractions. Okay. Now let's come to this part. P naught minus Ps by P naught equals to number of moles of solute. That means weight of solute by molecular weight of solute into number of moles of solvent. Means here weight by molecular weight. Molecular weight comes to the numerator. So molecular mass by weight of the solvent. This is the relative lowering of vapor pressure with the mass and molar mass of the both solute and the solvent. And remember that if by using this formula, we get the closest value, but not exact value. Why? Because here we neglected the N2 value from the denominator. If you don't want to neglect that also, if you want to get even for a constant solutions also, if you want to apply the Raoult's law, then instead of the P naught here, you take the Ps. So that P naught minus Ps by Ps is equals to weight of solute by molecular weight of solute into molecular mass of the solvent by weight of the solvent. So this formula is applicable for all type of solutions, by whether they are concentrated or diluted, but this is applicable for the diluted solutions only. Now let us see how this is related to the molality. We know that molality is equals to weight of solute by molecular weight of solute into 1000 by mass of the solvent. Now you send 1000 this side, we'll get m divided by 1000 is equals to weight of solute by molecular weight of solute into 1 upon weight of the solvent. So in this area, you can see that weight of solute, molecular weight and weight of the solvent. Weight of solute, molecular weight of the solute and weight of the solvent. In this area, we can substitute m by 1000. So that here this formula can be written as P naught minus Ps by P naught is equals to m, that means molality, into this is molecular weight of solvent divided by 1000, this 1000. So this is the relation between the relative lowering of vapor pressure and molality of the solution. So dear students, I hope you understand today's class. We shall meet in the next class, and the remaining part of this contents shall be discussed there. And as I promised you that how the relative lowering of vapor pressure is independent of the temperature, that I will tell you now. You see that here P naught minus Ps by P naught is equals to mole fraction of the solute. Mole fraction has no units. Relative lowering of vapor pressure also having the no units. Mole fraction is independent of the temperature. Since it is equals to relative lowering of vapor pressure, relative lowering of vapor pressure is also independent of the temperature. So this is of today's class, and we shall meet in the next class. Thank you one and all.